You are looking at Earth's most powerful force of nature, a supervolcano. And today, we're going to talk about whether we can stop one. There have been 3 known supervolcanic eruptions in Earth's history, the first of which happened about 74 million years ago. The next 2 both occurred within the past 2 million years, and the youngest of these 2 happened just 26,500 years ago, meaning that our species, Homo sapiens, has been around for nearly 1% of all time. Yet over half of that recent history has been dominated by these volcanoes. The first of these younger super-eruptions was the Oruanui eruption in New Zealand, which ejected over 2,800 cubic kilometers of ash and pumice. This volume is so massive that even if you were to spread it out evenly across the entire surface of the Earth, you would still be left with a layer of debris nearly 80 meters thick. The second super-eruption was the Mount Toba eruption in Indonesia, which was even larger than the Oruanui eruption, ejecting an estimated 2,900 cubic kilometers of debris. But while the Oruanui eruption occurred over a time frame of about 600 years, the Mount Toba eruption happened very quickly, mostly within a single day. It is thought that the Mount Toba eruption caused an ice age that lasted for 1,000 years, with some estimates suggesting that temperatures dropped as much as 5 degrees Celsius below normal. While these numbers may sound small, keep in mind that this is over the course of the entire planet. So a drop of 5 degrees may not sound like much, but it's the same thing as saying that you raised your car 10 feet off the ground, even though you only lifted it 0.00015 inches. Basically, this drop in temperature was global and extreme enough to influence the course of history. But despite these 2 recent eruptions, it had been remarkably quiet until just recently. That is, until April of 2021, when the world's largest active supervolcano began to rumble back to life. And while scientists don't expect the Yellowstone supervolcano to erupt anytime soon, they do predict that eventually it will. And when it does, the consequences could be catastrophic. In this video, we'll explore how supervolcanoes work and what happens if we could stop one. In order to understand what happens if we stop a supervolcano, we need to know what happens when one erupts. But in order to understand that, we first need to know what a volcano is. Put simply, a volcano is a rupture in the Earth's crust that allows hot molten rock called magma from deep within the planet to escape. As magma makes its way up through the Earth's crust, it often cools and hardens, which forms igneous rocks rich in silica. These igneous rocks are then pushed up further by more magma until they eventually form a mountain-like landform. When there's enough material piled up, this landform might become a volcano. Volcanoes come in all shapes and sizes, but they are all categorized into one of 5 different types based on their structure and how they erupt. The most common type of volcano is a shield volcano, which tends to be large in diameter with gently sloping sides. Shield volcanoes are created from low silica lava that flows easily and doesn't travel very far before cooling. Because of this, they tend to build up over time and create wide bases. If you can picture a warrior's shield lying flat on the ground, you can see why these volcanoes are named shields. The opposite of shield volcanoes are cinder cone volcanoes, which tend to be much smaller and steeper with loose materials that are easily blown away. Cinder cone volcanoes are made from high silica lava that doesn't flow very far before cooling. Because of this, they tend to be small and conical in shape. As the lava is blown away, it forms a cone around the vent, which is the opening where the lava comes from. If you can picture a pile of cinders blowing around in a cone shape, you can see why these volcanoes are named cones. Most volcanoes fall somewhere between these 2 extremes, being a mix of both shield and cinder cone volcanoes. These are called stratovolcanoes, and they tend to be the most dangerous type of volcano because they contain both runny and gooey lava, which can travel far and wide before cooling. Stratovolcanoes also tend to be tall, creating a column for gases and pressure to build up. When too much pressure builds up inside a stratovolcano, it can cause an explosive eruption. It should be noted that not all volcanoes are created in the same way. Some are actually formed when magma intrudes into existing rocks rather than when it erupts onto the surface. These are called plutonic or intrusive igneous bodies, and they can form batholiths, stocks, dikes, and sills. While these structures aren't technically volcanoes, they're still important because many famous volcanoes started out as intrusive igneous bodies. For example, the entire route of Mount Vesuvius began as a magma chamber that intruded into older rocks. Over time, layers of lava built up on top of this magma chamber until it formed the volcano we know today. So now that we know how volcanoes are formed, we can talk about what happens when a supervolcano erupts. A supervolcanic eruption occurs when a large volume of magma is explosively released into the atmosphere, causing massive devastation in the surrounding area. It's important to note that the term supervolcano doesn't refer to the size of the volcano itself, but rather to the size of the eruption. Any volcano can have a supereruption, and there are currently 12 known potentially supervolcanic centers around the world. To define a supereruption, geologists use something called the Volcanic Explosivity Index, or VEI. The VEI is a logarithmic scale that ranks the violence of volcanic eruptions based on several different factors, including the height of the eruption column, the volume of material erupted, and the length of time over which the eruption occurs. The VEI ranges from 1 to 8, with 8 being the most violent. By this scale, any eruption with a VEI of 8 is considered a supereruption. However, it's important to note that the VEI is a relative scale, which means that there's no exact threshold for what counts as a supereruption. Instead, it's a qualitative scale that describes the relative severity of different types of eruptions. For example, an eruption that ejects more than 1,000 cubic kilometers of material would likely be classified as a VEI 7 or 8, whereas an eruption that ejects less than 1,000 cubic kilometers of material would likely be classified as a VEI 6. But again, these numbers are just guidelines. Ultimately, it's up to geologists to decide how to classify a particular eruption based on the available evidence. When a supervolcano erupts, the initial explosion is only the beginning. In the days and weeks following the initial eruption, vast amounts of ash and debris are ejected into the atmosphere, which can travel around the globe. These fine particles can reflect sunlight, which can lead to global cooling. Additionally, the eruption can inject large amounts of gas and aerosols into the stratosphere, which can block sunlight and disrupt weather patterns. These effects can persist for months or even years, leading to what is known as volcanic winter. So what would happen if we stopped a supervolcano? Well, the answer depends on what causes the supervolcanic eruption in the first place. There are 4 main factors that contribute to supervolcanic eruptions: magma supply, gas content, viscosity, and driving pressure. Magma supply refers to the amount of magma available to fuel the eruption. Gas content refers to the amount of gas dissolved in the magma. Viscosity refers to the resistance of the magma to flow. And driving pressure refers to the pressure that builds up in the magma chamber. If the magma supply were cut off, the magma chamber would gradually empty, reducing the driving pressure. However, there would still be enough gas and magma left over to cause a large eruption. If the gas content were reduced, the magma would be less likely to expand and explode, but again there would still be enough gas left over to cause a large eruption. If the viscosity were increased, the magma would be less able to flow, increasing the driving pressure and possibly leading to a more explosive eruption. If the driving pressure were reduced, the magma would be less likely to expand and explode. This leads us to a very important concept in volcanology: the critical gas content. The critical gas content is the minimum amount of gas required to drive a magma to explosive eruption. If the gas content is below the critical gas content, the magma will not explode regardless of other conditions. Therefore, if we could reduce the gas content of a magma below its critical gas content, we would successfully diffuse the supervolcano. However, this is easier said than done. One promising approach is the use of nanoparticles. Nanoparticles are tiny particles that are 100 times smaller than the width of a human hair. They have unique chemical and physical properties that make them useful for a variety of applications, including diffusing supervolcanoes. When nanoparticles are injected into a magma chamber, they can react with the gas dissolved in the magma to form bubbles. These bubbles can then float to the surface and release the gas, reducing the gas content of the magma. Scientists have tested this method in laboratory settings and have found that it can effectively reduce the gas content of magma below its critical gas content. However, this method is still in the research phase and has not yet been tested in the field. Another promising approach is the use of a sonic device. This device uses sound waves to create bubbles in the magma chamber. These bubbles can then float to the surface and release the gas, reducing the gas content of the magma. Again, scientists have tested this method in laboratory settings and have found that it can effectively reduce the gas content of magma below its critical gas content. However, this method is also still in the research phase and has not yet been tested in the field. So while we have some promising leads, we are still a long way from being able to actually stop a supervolcano. If you enjoyed this video, be sure to check out my other content where I explore the weird ways the human body works. Thanks for watching.